Now that we have learned how to draw structures of different molecules in 2 dimensions, we're going to figure out, using those structures, what they look like in 3 dimensions. And these are known as the molecule shape, and we use the theory of Vesper to understand how this happens. So Vesper stands for valence shell electron pair repulsion. And this theory tells us that electron groups are going to try to stay as far apart as possible so that they reduce their repulsion. So electrons all have negative charges, so the closer together two electron groups are, the more repulsions they have. All right, and then the geometry that forms from this separation is called the electron group geometry. And for our purposes, we're going to learn just 3 different electron group geometries and then the molecule shapes that go with them. But you should know that for cases where we have an expanded octet and you have more than 4 things attached to your central atom, there are other options as well. If you take AP, we'll learn about them there, but we're not going to cover them in this class. All right, so if we have 2 electron groups, the best way to get those things as far apart as possible is to have them be 180 degrees apart. All right? So in a straight line like that. So then the angle would be 180, and this electron group geometry is called linear, all right, which should be fairly obvious, I think. So this is what we have when we have one central atom and we have 2 things attached on either side of it. All right, so let's say that we have our central atom has 3 things attached. So this could be 3 atoms, which is what I'm going to draw, or it could be that one of these groups is instead a non-bonding pair. And we'll talk about how that changes the geometry on the next slide. But in order to get these 3 things as far apart as possible, the easiest way to do that is, or the only way to do that, is an angle of 120 degrees. All right, so this is a flat molecule, and each of the 3 atoms or electron groups are separated by 120 degrees. And so we call this a triangular planar geometry. And that's because it makes a triangle if you attach the outer 3 atoms and it's in a plane, it's flat. All right, and then the last one that we're going to talk about is when we have our central atom and it has 4 things attached. All right, and this is the hardest one to draw. So this wedge means that it's coming out of the plane of your screen, so it's sticking out at you, and these dashed lines mean that it's sticking back into your screen in the other direction. And we're going to look at 3-dimensional models of these in class and also simulations, so hopefully you can get a good idea of what that looks like in your mind, but you should know how to draw them like this for quizzes and tests. All right, and the angle here, this is the one that's hardest to remember, is 109.5, all right, and that just happens to be the angle that all of them will be at to be equidistant from each other, which is as far apart as they can be. Okay, and this electron group geometry is called tetrahedral, and that's because if you connect all of the outer atoms, you get a tetrahedron. And one way that might be helpful to remember this, we've already had the tetra prefix before in class, and so maybe that can help you remember that that's when you have 4 things attached. So what happens if some of those groups are not atoms but are in fact non-bonding pairs? And so this is how we get other potential geometries. So the ones I just told you about were linear, trigonal planar, and tetrahedral. In the linear case, even if we replace one of these with a non-bonding pair, we still have a linear atom, so that one doesn't change. And for the trigonal planar, if we were to replace one of these groups with a non-bonding pair of electrons, we wouldn't see it, but it would cause repulsion and cause these other 2 atoms to come down out of the plane. So that is called bent. So if you imagine the trigonal planar where you just can't see the top one, what you would get is a bent structure like this. All right, and if we have just one non-bonding pair, then this bent angle will be pretty close to 120 degrees. All right, and then the last one we did was tetrahedral, and so in the case of tetrahedral, we could have one of the groups be replaced by a non-bonding pair. And if we did that, basically what we'd end up with is a little tripod with nothing sticking off the top, and that's called a trigonal pyramid. So it looks very much like the trigonal planar, but trigonal pyramidal is not flat. When you sit it the model on the table, it wouldn't sit flat. It would stick up like a tripod. All right, and then we could also replace two of those with a non-bonding pair, and then again, all you would see is these two that are forced closer together because of these electrons up on the top that are creating repulsion. And in that case, again, we'd have a bent molecule. So we have two different types of bent. One has an angle pretty close to 120 degrees, and the other one has an angle pretty close to 109.5 degrees. All right, so these are all of the molecule geometries, and I understand that it might seem overwhelming. You do have to learn these names because we're going to use them all the time, and it's important that you know the nomenclature. So if you remember them systematically, like I just went through them, it's really not that much to remember, and I'm hoping that with practice you'll find that it's not too tedious. All right, so now how do we determine what kind of molecule shape a given molecule will have? So first, let's start with CO2. So the first thing that we need to do always is draw the Lewis structure. Right, so carbon has 4 valence electrons, and oxygen has 6, but we have 2 of them. Right, so altogether that gives us 16 electrons. Okay, so carbon is going to go in the middle because it's less electronegative than oxygen. All right, and we're going to start with a bond to each oxygen. Right, so that's 4. Now we're going to do 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so we've used up all of our valence electrons, and all of our oxygens have 8, but each of our carbon only has 4, 2 from each bond. And so in order to make carbon happy, we're going to have to do a little more sharing. So we end up with, double bonds and then 2 lone pairs on each oxygen. All right, so now when we determine molecule shape, we want to know how many things are bonded to the central atom and how many non-bonding pairs does it have. All right, so carbon has let me switch colors. So carbon has 1 oxygen and 1 oxygen, and it has no non-bonding pairs. It doesn't matter that there are non-bonding pairs on the oxygens. We're only looking at the central atom, which is carbon. Okay, so carbon has 2 electron groups, all right, which means it's going to have a linear electron geometry. Okay, and since it has no non-bonding pairs, the molecule geometry is going to be the same as the electron geometry. So carbon dioxide is linear. All right, so now let's do formaldehyde. So hydrogen, we have 2 of them, and they each have 1. Carbon has 4, like we just did, and oxygen has 6. So if we add those together, we get 12. Okay. Carbon is less electronegative than oxygen, and hydrogen can't go in the middle, so we're going to stick carbon in the middle. We're going to put each of the other atoms around it. All right. Hydrogen's good. It's got 2, so it doesn't need any more. And we've used up 6 electrons, so we have 6 more. So that'll be 1, 2, 3, 4, 5, 6. So now oxygen has a full octet. Carbon only has 6 electrons, though, so we need to take a pair and move them in. All right, so we'll end up with a double bonded oxygen and a carbon with 2 hydrogens on either side. All right, so our central atom is carbon, and it has 1, 2, 3 things bound to it, and no lone pairs. All right, again, it doesn't matter that one of these is a double bond and one is a single bond. What we're counting is how many atoms are connected. All right, and so with 3 groups, that'll make our electron geometry trigonal planar. And since we have no non-bonding pairs on our central atom, that means our molecule geometry is going to be the same. It's also trigonal planar. Okay, so SO2. We did this one in our last video, but let's do it again just for review. So sulfur has 6 electrons, 6 valence electrons. Oxygen also has 6, but we have 2 of those. So that gives us a total of 18 electrons. So we're going to put sulfur in the middle. It's less electronegative than oxygen. Right, and then we'll put an oxygen on each side. Right, and we have 18 more to go around. We've used 4, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, and then in this case, we have only 6 electrons on the sulfur, so we're going to need to do some sharing. And so if you remember, this is one of those cases where we could share from this side, or we could share from this side, and so we end up with resonance. So we have sulfur with a double bond there, or we can get a single bond on this side and a double bond on this side. All right, and either of those are acceptable. In this case, in both situations, we have the same number of groups. So we have one atom bonded, one atom bonded, and one atom bonded, and one atom bonded over here. Because again, the double and single bonds don't matter. All right, and then in this case, our sulfur has a lone pair in both cases. So in both cases, we have 3 electron groups, which means our electron geometry is going to be trigonal planar. And what that tells us is that the angle between these oxygen-sulfur-oxygen bonds is going to be 120 degrees. All right, but we can't see that lone non-bonded pair on top of the sulfur, and so the geometry for the molecule is going to be bent. All right, so we have a bent molecule with an angle of approximately 120 degrees. All right, CH4, let's do this one. So carbon has 4 electrons, and hydrogen has 1, but we have 4 of them. All right, carbon's going to go in the middle because hydrogen can't. Excuse my handwriting this morning. And sorry, that's a total of 8 electrons. We have 2, 4, 6, 8. So we're all done. Pretty easy. All right, and this has 4 electron groups. 1, 2, 3, 4. Right? There's no lone pairs on the carbon. All right, and so our electron geometry is going to be tetrahedral because that's the one with 4 things attached. And since we have no lone pairs, our molecule geometry is going to be the same, so it's also going to be tetrahedral. And we draw that like this. That's our central atom. Remember, 2 of the atoms are in the plane, and then 1 is coming out, and 1 is going back in. All right, and that's how we draw that. All right, NH3. So nitrogen has 5 valence electrons, and hydrogen has 1, but we have 3 of them. So that gives us 8 altogether. So we have our nitrogen, 1, 2, 3 hydrogens. All right, and that's 2, 4, 6 electrons. We have 2 more left, and they're going to go on the nitrogen because each of the hydrogens is already happy. Okay, so if we count up our electron groups, we have 1, 2, 3 things that are bonded, and 1 lone pair. All right, so that's a total of 4. So our electron geometry is going to be tetrahedral. That tells us that our bond angles are always 109.5, or approximately. But in this case, we can't see one of the groups. So then, rather than it being tetrahedral, in this case, we're going to call it trigonal pyramidal, and remember, this is how we would draw it. And so this is because we have that non-bonded pair up here that we can't see, but is forcing these 3 atoms down out of the plane. Right? So this is trigonal pyramidal, or a trigonal pyramid. All right, water. So water is H has 1, and we have 2 of them, and oxygen has 6. So altogether, that's 8 electrons. Oxygen has to go in the middle. We'll bond both of our hydrogens. All right, so we've used 2, 4 electrons, and we have 8 total. So we're going to do 5, 6, 7, 8. All right, everybody has, the oxygen has an octet. The hydrogens both have 2, so they're happy. All right, so let's count up our electron groups. We have 2 bonds, so that's 2. And then we have 2 pairs that are non-bonded. So that gives us 4 altogether. So our electron geometry is going to be tetrahedral again. So we know our bond angle is right around 109.5. But we have these 2 lone pairs. So 2 of our groups we're not going to be able to see. So if we were to draw it, it's going to look like this, with this angle being about 109.5. Right? And this is called bent. Right? So our molecule shape here is bent. All right, so that wraps up our discussion of molecule shapes and molecule geometries. Like I said, we're going to spend some time in class using models to help give you a better idea, but you should practice drawing these, particularly the ones that use the wedge and the dash, tetrahedral and trigonal pyramidal, because being able to draw those properly on a test or a quiz is very important. You can't just draw them with regular lines because then that implies that they're in the plane and they're not. So we want to be able to draw them with a correct representation.